We're going to calculate the internal resistance of a D-cell battery, and we're going to put together different circuits and measure the current and voltage in a particular way, and the circuits include one or more known external resistors. And here's a diagram of your circuit: voltmeter, ammeter, the cell with the lowercase r being its internal resistance, and the capital R being a known external resistor in the external circuit. A little bit more information here: voltmeter in parallel to the cell, ammeter in series with the cell, and pause to look at this as long as you need to. And here's the equipment that we have: the battery holder, the multimeters and resistor. And you can look at the photograph here, which shows the actual setup for each of those items, and the circuit diagram as well. And you're going to do this experiment with different resistors in the external circuit, the same battery with the same internal resistance each time, and you're going to note the external resistors. They're written on there, and you can have them in series as shown here, 2 or more. You can have them in parallel as shown here.
To do the analysis, you've got to assume that the resistance of this battery stays constant for the whole experiment, which it should, because it's only going to take like a few minutes. To make sure that happens, you don't want to leave your circuit connected for too long. So you're going to get it set up, you're going to make the readings, and then disconnect it. So for 2 reasons: one, it's going to run down the battery if you leave it connected. The other, you're going to use resistors, and what resistors do is they change electrical energy into a different kind of energy. Do you know what kind of energy? Heat. Yeah, it changes into heat energy. So you're going to be producing heat. It's a small amount of heat, but over time, the heat is going to build up. Positive side up. Whoops, hold it the right way. Positive side up, and you're going to make sure it works. So if you're in the green zone, it's a good battery. So you're going to need a voltmeter, you're going to need an ammeter, and the thing in the circuit that's going to be using up the electricity, the electrical energy, is going to be these resistors. So these resistors, they look like this. These in the holders. So you're going to put it in the holder like this, and once they're in the holder, you really don't have to touch the resistor. The other reason this is good is because the resistor is going to get warm, maybe hot if you leave it connected too long, and you don't want to burn your fingers. The leads should fit in here to connect them, so that one can clip on there. So there are 1 ohm, 10 ohm, 50 ohm, and 100 ohm resistors. But Mr. Godwin has written up for you. He'd like you to get as many data points as possible. You can hook them up in series and in parallel, and in combination you like, to get different amounts of resistance. Yeah, so usually the biggest problem when you're making circuits is just bad connections. So if things don't seem to be working right, just check all your connections, make sure they're solid. If I've got a 1 ohm resistor or a 100 ohm resistor, and I hook it up to the same battery, you can say it out loud. Which one do you think will get higher? No? I guess? 100. 100? Why do you think it's 100? Okay, so here's the truth. It's a good guess. The 1 ohm resistor is going to allow more current, and it's the current that creates the heat. So when you have a lot of current going through the circuit, you're going to get a lot of heat. And a 1 ohm resistor is going to get 100 times more current than a 100 ohm resistor. So it's the 1 ohm resistors that are the ones you got to be careful with. Internal resistance is little r. Okay, uppercase R is the resistance of this outside of the battery, and the little r is questions before we start? Okay, so everyone can bring.
Is that right?
That looks good. So now, so this is going to give you the potential difference here.
Yeah.
That's going to be the current going through here. And then you just got to get these in the right spots.
Is it? Which
That's the one,
Okay.
yeah.
That's good. I think it's dropping a lot of current.
And with your data, you're going to write down the external resistor values in ohms, the voltage reading of the voltmeter going across the battery in volts, and the current passing through the circuit in amps. And with that data, you're going to process it, and useful equations, Ohm's law, and the fact that the EMF of the cell in volts equals current times the internal resistance plus the current times the external resistance, and that can be those can be combined to give EMF equals I times the internal resistance plus V, and a reminder at the bottom how to work out the sum of resistors in series or indeed in parallel. And just going through that those formulas again, pause as long as needed. And we're going to process the data by plotting a graph of the terminal voltage and against the current in the circuit. So what, looking at your results, do you think you have got here? And if we plot a set of results, you've got the data in a line that's going downhill. So add your line of best fit and you've got a straight line. So what's the relationship between the terminal voltage and your current reading? So it's the equation of a straight line, y equals mx plus c, and m is the slope, the cell's internal resistance, and goes downhill, so we've got minus m being equal to r, and your slope is rise over run. So how will you find the EMF of your cell? From your graph here. So what you're going to do is extrapolate the line of your graph to the y-axis, and that will give you your EMF of your battery in volts. Now, question here to pause and predict and explain what you think will happen to a cell's internal resistance at low temperatures and indeed at high temperatures. And here you've got some descriptions of different types of batteries. The alkaline battery on the left is the D cell used in the lab. In the center you've got a nickel metal hydride rechargeable battery, and on the right you've got a lithium ion also rechargeable battery. And what I want you to do is to compare the anode and cathode equations for the batteries discharging, doing work. The rechargeable ones, the reverse direction will give you the charging equations. What is the nature of the anode and cathode, the electrodes in all of these batteries, and indeed what is the electrolyte. And out of interest, here we have a lithium ion battery in a Mars rover, and you can use the QR code or the URL to find out more about Curiosity. And in aircraft, different batteries in different types of aircraft, but the nickel metal hydride batteries are rarely used because here it says require more gas emission monitoring than NiCad, nickel cadmium, and those that's because you're going to produce some hydrogen. So many thanks to Mr. Jollymore and the physics students at Washington International School. Thank you.